Our first speaker is Lorna Kotz, who is our co-organizer of these sessions from Denver Water, and she's going to tell us about climate adaptation at Denver Water.
Great. Thanks, Russ. I didn't actually learn how to use the clicker before I came up here. Okay, got it. Okay, so I'm going to talk about Denver Water's climate adaptation work. I've been with Denver Water for a little over a decade and working on climate adaptation for longer than that. So I'm excited to be here and share our story with you guys today. Many of you in the room just played a game with us, and that was the Game of the Decades. So I'm going to walk through our case study and then tie it back to the game because we have a really, really analogous story. So just really briefly, Denver Water is the largest water utility in the state of Colorado, and we're also the oldest. We serve a quarter of the state's population drinking water. And in the teal area, we have our service area, which is the city and county of Denver, and some suburban customers. And in the black area is our collection system. So the yellow and black dotted line is the Continental Divide. So you can see that we have a high elevation collection system. So much of what we learned this morning about warming, about the implications of warming, they're not as prevalent high elevation, but they are starting to happen. We're starting to see rain on snow. We're starting to see a little bit of rain instead of snow. But it's not happening to the same degree that it is taking place across places like the Pacific Northwest or places with lower elevation watersheds that still rely on are still snow dominated. So it's good lessons for us to see and learn from because, as you know, we're going to continue to warm, and that's something we need to be prepared for. Okay, everyone I think in this room is familiar with the 2002 story. Some of you were managing and lived through the 2002 events. And in 2002, we experienced the single driest year on record. Since then, we've also experienced 2012, which was nearly as dry, or in some places even drier. At that same time, in that same year, so the dry year starts in June, we experienced the worst wildfire the state has still to date ever experienced in our workhorse watershed. That fire went out in July. Fast forward 3 or 4 weeks, and we get a business as usual rainstorm. It's not an extreme rainstorm, it's just your business as usual summertime rainstorm. And all of this debris and ash and sedimentation comes down into our reservoirs. So here's a picture of some folks on a raft trying to clear the top of Strontius Springs. So we're in a drought. We just had a nasty fire, and we have to flush some of this water because we can't treat it. It's filled with ash and debris, and it was pretty devastating. It was a good learning experience for us, and of course we all are familiar with the watershed changes that we're experiencing across the state with beetle kill and whatnot. So change was in the air, and our first question was, like we heard this morning from, went too fast. The last slide was a very good slide on paleohydrology. Our first question, thank you, was is this natural variability? So it's not that we had never expected to experience wildfires. It's just we didn't expect to experience the worst wildfire and the worst drought, single year drought, in the same year in our watersheds at the same time. So that's what was devastating for us. So we said, okay, is this natural variability? Are we just not prepared for what our region has experienced in the past? So we worked with Jeff Lucas, actually, and Connie Woodhouse to extend our hydrology data back in time to 1634. So this goes from 1634 to 2005. And this is storage data. So it doesn't show you how wet it could be. It just shows you that we fill. But we also see that there's periods in time. So here's 2002, the 2002 dip. If you go 3 dips over, that's 1950s. But then you cruise over to the 1800s, and those are wicked nasty, right? It's an extended period of drought. It's really intense. And you go back to the 1600s, and there's some nasty things that took place too. So we learned that we weren't fully preparing for the variability that our region has experienced. The next question is, well, what could we be up against in the future? And we turned to look at climate science and climate models, and we did a sophisticated analysis with a group of other Front Range water utilities to better understand what climate change or what the future climate could look like so that we could know what our region could be experiencing. And this is what we call our shotgun graph, because we really thought science was going to solve this problem and not give us like, well, climate change means 6. You know, I mean, we kind of were hoping we get a single number, frankly. But we weren't expecting a scatter plot like this, right? Where we see our region could warm 1 to 10 degrees Fahrenheit, right? Or precipitation could increase 30% or decrease 20%. That's a huge range of possibilities, right? So what do you do with that? And, you know, frankly, I'm a scientist, so I was disappointed in science. So our first thing was that we started investing in science. We're like, science is going to solve this problem, and we got a lesson in uncertainty. But one thing I want to note is that all of these climate models are suggesting that our region is going to continue to get warmer. Right? So we took a step back and said, okay, what does warming mean to our system? And this is what I encourage everyone to get a bumper sticker of or shirt. WWWM, what will warming mean? I think this is a foundational question to thinking about what climate change can mean to your system. We know we're warming, we're observing warming, and we're going to continue to warm. What does that mean on the ground? And for us, we learned that we're incredibly sensitive, right? It's not rocket science. We have a snowpack-driven system. If it heats up, it's going to dry out a little bit, right? It's a surface water supply. So we did analysis in 2005, 2011. Each iteration was a little bit more sophisticated. And we see we could lose 1/5 of our supply from 5-degree warming. And we've already warmed probably over 2.5 degrees, or 2 degrees now across our state. So then we asked, well, how much would precipitation have to increase in order to offset this warming? And we found we would need precipitation in our state to increase 10%. That's huge, right? Is that going to happen in a semi-arid region? I mean, maybe, right? A warmer atmosphere can hold more water. On an annual basis, are we going to get 10% more water? I don't know. I don't know if I'd bet on that. Although we could use the dice, I guess. So most recently, we started to, and this is in the green box at the bottom, we started to tease precipitation in there as well. So we looked at an optimistic future where we warm 3 degrees and winters get wetter, but we see we're still vulnerable. Our supply decreases 5%. And then we also looked at a more pessimistic scenario, more of the trajectory that we're on. Let's say we warm 6 degrees and daily events become more extreme. So every time we get a precipitation event over an inch, it's a lot bigger, but everything under an inch is a lot smaller, so that every year is the same. We have no change in annual precipitation. It all evens out. We're just increasing the daily variability. And we see we're even more vulnerable in that case. So the extreme precipitation may help us, but it depends on if it drops. And it also depends on if those smaller storms actually make a difference in drop water. So what we're trying to avoid is this situation where we've looked to the left and we've looked to the right and we think that we've planned and figured out everything that we could be up against, but we haven't looked full all the way around, and there is a shark headed our direction. So many of you know this, but one of our next big steps was to start using a process called scenario planning. And the state of Colorado has used this in their state water plan. Bureau of Reclamation uses this in their supply and demand study. And the whole idea is that we needed to take a step back and say we don't know what the future is going to look like. We can't predict what it's going to look like. And we can't extrapolate current trends to depict what our future is going to look like. There are things outside of our control that are going to change the way our future comes to fruition. So let's play with those. Let's think about how things outside of our control can come to fruition to create different futures, different ways the world could be than what we're in now. So we looked at 4 different futures, and the idea is you come up with a plan for each of those futures, and then near term, you have commonalities, and you invest in those commonalities, and those investments set you up for being prepared for a range of possibilities. So this slide is really important, and I'm not going to spend too much time on the details, but we had 3 drivers of change these are things that are outside of our control that we use to come up with our futures. And these are futures that we're saying this is how the world could look. On the y-axis, we have climate. So we're saying climate is outside of our control, but we need to be prepared for a warmer or a hotter future. We're not saying we need to be prepared for a historical climate. We're saying it's going to be warmer or hotter. So we're making a statement that climate change is here and now, and our region is going to continue to warm. We're also saying we can't control the economy, right? It could be a really strong economy like what we're in right now. It could be a super weak economy like we experienced in the late 2000s. And we also can't predict what's going to go on with social values. You know, how are people going to want to live? Where are they going to want to live? Are they going to want to live high density? Are they going to want to have single family households? Are they going to want to have lawns? Are they just want to have parks, right? So that type of uncertainty, these are the 3 uncertainties that we looked at. And our objective was to create an adaptive plan that included diversified portfolios. So this means geographically diverse, as well as the type of option that we're diversified in. Scalable options, so things that we could increase in capacity if we need to in the future. Preserve options, so that we have them available for us in the future if we need them, but we're not fully investing in them now. And our whole objective is to build flexibility. So we're building flexibility in our investments and in our operations. So 4 projects, 4 examples is we're in the lower part of our system, we're bifurcating a water treatment plant. So we're adding a train, we're breaking the train in 2. So we're adding flexibility to that treatment plant. In the northern part of our system, we're building a new treatment plant, but we're not building it to the full capacity it could ever be, the largest capacity we may ever need. We're building it to a smaller capacity, but putting in some infrastructure so if we need to expand it in the future, we can. We've invested in our watersheds, and many of you know how many fires took place last year. We had a pretty nasty one in Buffalo Mountain. And we estimated that we saved nearly $1 billion in infrastructure, in property, and in lives with the work we've done with our From Forests to Faucets program. And then finally, we're expanding a reservoir in the northern part of our system. Most of our reservoirs are in the southern part of our system, so expanding a reservoir in the northern part of our system helps diversify our portfolio geographically. So, connecting us back to the game. So some of you played the game, some of you didn't, so apologize for those who don't know what I'm talking about. But decade 1 in the game, you guys remember we had the 6-sided dice. Everyone knows how a dice works, right? You can play the odds and maximize your return. That was us pre-2002, right? We're thinking in firm build out, we're thinking about firm yield and build out demand, right? We're assuming history is going to repeat itself into the future, and we really know what firm yield is. We're also assuming that we would build out to our city limits, and then our demands would stop. We would plateau. So we'd know demand and supply, and we'd be sitting really fat and happy. Along comes decade number 2, right? And we turn the table on you a little bit by taking away your dice that you understand and replacing it with another dice, right? And it probably didn't seem fair. When I first played the game, I didn't think this was fair. I didn't think it was nice. I was irritated. But I still played with the rules because there were rules, right? I understood, right? 6, 7, 8, right? Did I get that right? Or 6 meant a flood, a 1, 2, and 3 means a drought, right? So there's still rules that I understand. So this is kind of what happened to us in 2002, right? Something happened, the rules started to change, but we weren't exactly sure what it meant. Come along to decade number 3, well, we don't change the rules on you, but you don't know that, right? So for us, this is when we started to adopt the new ways of planning for the future, because we were nervous. We didn't want to experience something like 2002 again. We didn't want to feel like we were potentially unprepared or ill-prepared. We wanted to make sure we were prepared for whatever the future could bring. So decade number 4, right? Now we're dealing with this funky device. No idea how it works. Maybe it lands up, maybe it lands down, maybe it lands on its side. And we could spend our time and money diving into the science to understand how it will land, so it can be a predictive tool, or we can spend our time and money trying to prepare for however it lands. And that's really where we've gotten to. We are, within our organization, are really embracing uncertainty. We're seeking flexible options. We're not using prediction anymore for our long-term planning. And that's not to say that prediction isn't useful, especially for near-term decision-making, seasonal forecasts and whatnot. That's not what I'm talking about. I'm talking about more long-term. But we're not looking at past trends to represent future conditions. We're saying there's things outside of our control that are come to fruition in a certain way, and we need to be prepared for whatever that looks like. So I have a whole slew of lessons. Really quickly, we did a super simple assessment to look at how vulnerable we were to warming. It was incredibly informative. We're very vulnerable to warming. We learned that science can't solve this problem in the traditional sense. I'm still bent out of shape about that. But we know science can be really informative and has to be a player at the table. We need to be planning for multiple futures and not saying, well, we want our future to look like X. Rather, we want to be prepared for X, Y, and Z possible future conditions. And we want to be building adaptive capacity. So with that, I want to end on a group called the Water Utility Climate Alliance. I'm chair of the alliance this year and next year. We have a vision for climate resilient water utilities, thriving communities, and we're collaboratively advancing water utility climate change adaptation. We have dozens of reports. So if you have a climate question, we have a report on that. So I encourage you to go check out our website, WCAonline.org. This year, we're developing a best practices in climate adaptation product that will be done in March or April. We're also working on a project with Fort Collins to identify business practices that are at risk to climate and link climate information back to those business practices. So for example, HR could be, can be connected to climate because when your staff is going outside and you're having back-to-back-to-back 90-degree days, that is a public health concern. So climate change can be brought into many different areas within your organization. It's not just a supply challenge. We have a training that's held across the nation. The next one will be in Tampa Bay and then Austin. And then finally, we're also working on communication. As a scientist, my communication skills are not always the best, right? So we're learning how to better communicate about this politically heated topic and bring it into our organizations. So that's all I have. Thank you so much.
Thanks, Lorna. Time for one quick question, if there is one. Any? Okay, well, thanks, Lorna. All right, so our next speaker will be Taryn Finnessy, who's also helped to organize what we've been doing here today. Taryn is with the state of Colorado and the Colorado Water Conservation Board.
I'm going to put it here because I talk with my hands and I flail. And the last thing you guys need is a mic to the head. All right, so Lorna talked a lot about kind of how they got to where they are with Denver Water and the progression of their story and why this became an issue for them. It's really similar for the state of Colorado. I started with the state about 10 years ago, and we recognized that our method of water planning and looking to the past as a guide for the future was not going to be sufficient in going forward. We started looking at a number of science studies, but what I really want to focus on today is not the specifics of that science, which I think a lot of you have heard before. We've presented at Water Congress a number of times. With the Colorado River Water Availability Study, we did a whole road show, so a lot of you have seen that. So what I'm going to focus on today is what we're doing to incorporate that science into our efforts, the story that it tells, and then kind of where we go from here. So a little bit different twist on the science and the practice. So in Colorado, just generally, we want the best future for our citizens, for our land, for our economy, and climate change has the potential to impact all facets of our economy. This is the Colorado Resiliency Framework that was developed after the floods and the drought and the fires of 2013. But it really does a good job kind of capturing the different pieces of our economy. And climate change really does impact all facets of the framework. I didn't even practice that, huh? I may have said this once or twice before. Be it high temperatures or earlier runoff, increased fires in our watersheds, impacts to our agricultural lands, water and climate change is going to impact our economy in the future. So how do we make sure that we have enough water going forward for whatever our population may be? And I want to put out there that in the climate world, people have been crippled by this term of uncertainty. We've heard time and time again, the science is uncertain, so we can't use it. We'll wait until the next rendition. CMIP5 will give us more information. And what I'm here to say is that we make decisions in the face of uncertainty all the time. We have no idea exactly what our population is going to be in 2050. We can use science to make projections. We can make guesstimates about where our economy is going, or what our housing needs are going to be, or what our healthcare needs are going to be. But there's a lot of uncertainty embedded in that. We, as a society, embrace economics, and the first thing they teach you in economics is to understand the assumptions, because there's a whole boatload of them, and that's based on uncertainty, right? And so we make decisions based on uncertainty all the time. Climate change is no different. It's just understanding what the trade-offs are and what that means in your decision-making process. So this is kind of a variation of what Lorna showed. We might have poached a little bit from Denver Water in the development of this, but better not to reinvent the wheel, right? So when we started looking at how we were going to integrate climate change into our long-term water resource planning and how specifically we were going to integrate it into the water plan, we had a lot of discussions about, is climate change going to be its own standalone chapter? Or is it going to be this thread that's woven throughout the entire water plan? And John alluded to this earlier. Climate change, because it impacts all facets of our economy, really, it doesn't make any sense to have it in its own silo. So we want it to be this thread that weaves throughout the water plan. And in doing that, developing the water plan, we have these 5 scenarios that are actually somewhat captured towards the end. And I'll get to them in a second. But the 5 scenarios are trying to really capture the range of plausible futures. None of them are going to actually come to fruition, but just capture the range of possible futures. So whatever future may actually materialize, hopefully we are in a place where we can respond and react accordingly. So that's the idea behind scenario planning. Rather than planning for one static future, we are planning for a range of futures, and along the way we're going to make different decisions about how we're going to allocate resources and what pathway we're on. So in developing the water plan scenarios, this was a really kind of grassroots effort. All of the basin roundtables came up with their own different scenarios, and then we brought them together at the state level. We kind of combined the pieces that were similar and then culled it down to 5 scenarios that represented pretty much what those various basin roundtables had come up with. And there were a number of different drivers. This is kind of a distilled down, simplified version, which is really, really blurry. I'm sorry. But in 3 of those 5 scenarios, we used a perturbed climate. So 2 of the scenarios assumed that the climate going forward is 20th century observed, and the other 3 observe some kind of perturbed climate. So either hot and dry, or somewhere between 20th century observed and hot and dry. Those were the definitions that were given to us, which doesn't really help. Sorry to all the IBCC members in the room. But we had to define that. We had to figure out, what does that mean? What does hot and dry mean? What does somewhere between 20th century observed mean? And how do we actually apply that to inform our decision-making process? So we took as much information as we could from both CMIP3 and CMIP5. We were using all of the different projections, and we plotted them out together. We used kind of the crop irrigation requirement as a proxy for demand. and we plotted it all out. We plotted where we are with 20th century observed, and then we were able to define, based on an analysis using our 5 nearest neighbors, and I'm not going to go into the technical piece. There's a really good technical memo on this if you really want the details. But we were able to plot out and actually quantify what hot and dry means and what somewhere between 20th century observed means, and this is what it is. I didn't actually expect you to read that previous graph. It was just there for being pretty. This is equally as blurry. I have no idea what's going on. So what we were looking at was crop irrigation requirements and runoff as a means to kind of look at how this climate information plays out within our water systems. And you can see that we plotted up where our current 20th century observed is, and then where we actually decided not to go all the way to the extremes for our hot and dry. We could have chosen something down, I don't have a laser. We could have chosen like the most extreme version down here. But there is a difference between scientifically plausible and politically palatable. And we realized that. I mean, we were doing this 4 years ago, right? A lot of you might not have even come to a climate session at Water Congress 4 or 5 years ago. And so we wanted to make sure that what we were choosing as our hot and dry scenario was accurate, and it was hot and dry, and it was severe enough that it represented a plausible future, but that also was not so extreme that it was immediately cast off. And so we chose a representative plot or representative run that was dry. About 20% was more dry, but it represented about 80% of the swath. So 20% of the runs would have been more dry than that. And then we plotted the current, and there was no science to between 20th century observed and hot and dry. We literally said, ooh, that one looks like the middle. And it turns out to be right kind of in the middle of the 50th percentile for both. So that's how we were able to quantify that from the CMIP3 and the CMIP5 data, but then we actually took it and, okay, my slides are out of order, but we took it and we ran it through actual river models, through our water models, and we were able to see how it impacts flows. So I know you're all really anxious to see that, but stay tuned because now I'm going to talk about this slide for a second. I can't go back on my clicker. So in doing that, we're now also able to integrate that climate change, the climate change scenarios that were engaged or that were part of the water plan into our SWASI process. So the previous versions of SWASI, which I think last came out in 2010, did not have climate in it. In fact, prior to the water plan, when CWCB looked at the future, we looked at population growth and we looked at demand. We didn't even use a drought of record. And so we didn't really factor in those worst case scenarios. Now, by looking at those climate scenarios, by looking at that hot and dry, by looking at that somewhere between 20th century observed and hot and dry, we're looking at a much broader range of what the future might look like. Now that we're updating SWASI, we can go through and actually integrate that information into our SWASI process, and then that information can also be used by the individual basins to incorporate into their basin plans that they'll be updating again, because as it was mentioned earlier today, the water plan is an ongoing process. Thank you. Whoa. There we go. Okay, so when we ran this put this into our models to find out what it actually meant with regard to flows in our rivers and water availability, because that's what we were really trying to get at. We know temperatures are increasing. We know they are projected to continue to increase. We feel really confident about that. But what we wanted to know was, what does this mean for the water that we have within our systems statewide, and our overall availability? And what you can see is that in some of the most heavily appropriated river basins, the Arkansas, the South Platte, the Rio Grande, under some of the scenarios, at least in the Arkansas and the Rio, under both scenarios, climate perturbed scenarios, the hot and dry and the somewhere between 20th century observed and hot and dry. I need to come up with a good acronym for that because it's really a mouthful. We actually have no water available, not just to meet future demands, but to meet existing demands. Now, this is an oversimplified way of looking at it because it doesn't necessarily represent dry river conditions, because there could be a senior water rights holder down the river that is pulling water through the system. And so it's a little bit more complicated than when you actually just plot it out. But for all intents and purposes, we had always expected that future demands, we may not have enough water to meet future demands, but existing demands would be met. And that turns out to not be the case in some river basins under both climate perturbed scenarios, but then in the South Platte under the hot and dry. And this surprised us at first, but when we were doing this, it was right after the 2012 drought. And so I was really curious what happened in the Arkansas River Basin during the 2012 and how far back the calls went. And it turns out that in a single drought year within the 2011-2012 drought, there were calls back into, I think it was 1868. And that was one dry year. So it's not really all that shocking that these systems that are already stressed, that are already heavily appropriated, are going to continue to be stressed and heavily appropriated in the future. But what it does make us realize is that we have to think about how we utilize those water resources and how we allocate and work together to make sure that the demands that we have are being met. Ah! I just skipped over the water plan. John, I'm sorry. There we go. Oh, thanks. Can't skip over that. So what we've been doing is making sure that within the water work that we're doing, within the long-term water resource efforts that we have underway with CWC, we're integrating climate change as another layer of decision-making. So we're thinking about it when we think about population growth, we think about climate change, when we think about finance. It's just one more layer of decision-making that we utilize in looking at water availability and supply at the state as a whole. This is a similar approach to what we're doing statewide. Across a whole number of sectors, we're looking at climate change and trying to just institutionalize it such that it is another layer of our decision-making process. So that when you think back to that initial slide where I said, you know, our goal is to create a better future, a better, stronger future for the people of Colorado, we're addressing that not just within the water world, but across the whole state of Colorado, across a whole number of sectors. But we've gotten the furthest in the water world, and we understand what this means. And what we recognize is that in Colorado, climate change means water impacts. It means water change. And so we need to be thinking about this proactively, and we need to be thinking about mitigation strategies to reduce the overall impact of climate change, but then adaptation strategies to deal with the impacts that we're already seeing today.
Question for Taryn? Everyone's quiet this afternoon. No? All right. Well, let's thank Taryn. Our next speaker will be Ken Novak from the U.S. Bureau of Reclamation.
Good afternoon. I'm Ken Nowak. I'm with Bureau of Reclamation's Research and Development Office down in Lakewood at the Federal Center. My position is Water Availability Research Coordinator, so I'm responsible for coordinating research within reclamation and as well as outside of reclamation with our federal and state and other partners on water availability, everything from short-term stream flow forecasts, seasonal water supply prediction, to the long-term climate projections we've been hearing about today. My scope also includes the system models that go along with those various water availability predictions or projections. So I'm pleased to be here to share a few case studies from the reclamation side of things in terms of how we contend with uncertainty in water management looking forward Really quickly, I think most people are probably familiar with reclamation, but this is my 30-second orientation if you're not. Reclamation is part of the Interior Department. We operate only in the 17 western states. We're broken into 5 geographic regions, largely based on hydrologic boundaries, but you'll obviously see some straight lines that follow state boundaries as well. We're the largest water wholesaler in the United States, second largest producer of hydropower. We operate over 300 reservoirs. We provide 1 out of 5 western farmers with water to irrigate over 10 million acres of highly productive ag lands. A lot of folks wonder how we differ from our other major federal water management agency, the Army Corps of Engineers. The short of that is that reclamation is a water supply focused mission. The Army Corps of Engineers are concerned with flood control and navigation. So in addition to having a lot of reservoirs, we have thousands of miles of canals to get water to those fields and those cities that need it. So that's reclamation in a nutshell. You can see our mission at the top. All right, so I'd like to talk about 2 different activities that I think relate to this topic and this discussion. One is our reservoir operations pilots, an activity that's been ongoing for a couple years. And then another one is the Colorado River Basin Study. That was an effort I was involved with a number of years ago. Many of you are probably familiar with it. I don't think the results are necessarily new, but I think the methods are very relevant to this discussion. So I'd like to share that and then finally wrap up with a few summary remarks. All right, so our reservoir operations pilots are a relatively new initiative a couple of years ago, and it's focused not necessarily on traditional water supply planning, but rather reservoir operations. And so it's kind of a 3-legged stool is the way I like to present it. We're looking for ways to improve Western water management through better operations. And these pilots, one from each of our 5 regions, looked at 3 things or tried to evaluate them. The first is incorporating better scientific information. So this could be better data sets, better forecasts, better tools, better models. What can we bring into our decision-making process that's going to bring it up and result in a better outcome for our stakeholders and our management objectives? The second is better understanding and enhancing our operational flexibility. To operate better, you've got to kind of know your full latitude, and so evaluating that is pretty important as well. And then finally, this last bullet, I kind of summarize as sort of our chronic concerns. What are the long-term risks, the major concerns, climate change, reservoir sedimentation, changes in extreme flood frequency, those sorts of things that we need to be thinking about as we look to extend the life of, in some cases, infrastructure that's already over 100 years old. So one of our pilots has concluded. It's the Upper Washita. This is in southwestern Oklahoma, actually, so not Colorado, but I think it's helpful to use this to highlight the type of work that's going on in these pilots. As I mentioned, these pilots have been going on for a couple years, so when they were being identified, Oklahoma had just concluded a pretty severe drought, in fact. So 2011 to 2015 was devastating for that region, and if you look at this reservoir here, Foss Reservoir, those concrete structures are water supply intakes. The upper one is totally dry, and the bottom one is like sipping. I mean, barely getting water out. And so you've got pictures of, dry dead fish, dry boat ramps, all of that stuff that we've become all too accustomed to in the western U.S. And so really the focus of this pilot was to look at better improvements to long-term and short-term drought planning by incorporating new modeling tools and also new data sets. So I'll quickly highlight this. Using the sort of traditional approach for drought planning, the idea of a firm yield based on a drought of record. And so what this plot shows is on the x-axis, you've got a firm yield estimate, and on the y-axis, a drought duration. And the drought of record resulted in a firm yield that was just shy of 20,000 acre-feet per year. And while I don't think anyone would claim that it was 100% firm, there was sort of an implicit assumption that that's a reliable amount of water and we can probably depend on it with a good amount of certainty. That 2011 to 2015 drought sort of challenged that in a big way for most people. And so what they did was they brought in new modeling tools that allowed us to look at a lot of scenarios and also brought in new data sets that expanded the uncertainty and variability in our hydrologic conditions. Specifically, we looked at paleo-reconstructed data and techniques that have been developed at reclamation to actually further expand that distribution of likely conditions based on what we're seeing in the paleo-reconstructions. And so now we have a whole range of drought of records to look at. And so we can see that the previous drought of record was 14 years, and now we've got drought of records that exceed that by double. And the range of firm yields is considerable. And so if we look at this as a way to contextualize what we'd previously been planning for, not that this is necessarily the true distribution of the hydrologic conditions in the basin, but it tells us that what we've been planning for might be only 70% firm, to use that as sort of a term of art here, and that in some cases we could see a firm yield that's half that amount. And so this was really enlightening for folks. It really gives an idea of what the range of conditions might be and opens a discussion into uncertainty, whereas when you have a single value, you're really blind to the uncertainty. I think most people would say it's there, but they don't know it. So what do you plan for? I mean, that's really the art as we move beyond the science. The approach that they've embraced in this particular activity is a balancing act between risk exposure and risk tolerance. And where exactly you draw that threshold to take action is certainly something that remains to be worked out. But I think it's important that when you expose that uncertainty, you can more directly confront it and you can make better decisions. Whereas when you don't have that information, you're very limited in terms of what you might be able to consider. So that's our reservoir operations one case study that's been wrapped up. Now I'm going to pivot to the Colorado River Basin study. This is more of a traditional long-term supply and demand paradigm. Our basin study program funds basin studies across the western U.S. They've been done in most of the major basins. You may have seen them elsewhere, but I'm going to talk a little bit about the Colorado here. So the study approach was 4 major phases. The first is a water supply assessment. So what do we think the future might hold in terms of water availability? The second is a water demand assessment. What are the likely future demands on the system? You couple those together, you get some version of that cone of uncertainty that we've seen already. Phases 1 and 2 allow us to proceed to phase 3, which is a system reliability analysis. This is where we see how is the system performing under those various combinations of conditions, start to understand where it becomes vulnerable, what are those conditions, hydrologic and otherwise, that are associated with these vulnerable outcomes, and ultimately, can we identify precursors to them so that we can start doing things proactively rather than letting our reservoirs drop to a critical level or another undesirable outcome. And then finally, phase 4 is what can we do about it? So can we put together a portfolio of options that are responsive to these concerns, these vulnerabilities, and implement them in a smart way that doesn't overinvest but also improves our operational outcomes. So on the first 2 parts, supply and demand assessment, they kind of go hand in hand, so I'll cover them here together. The blue line to the left of the vertical dash is water supply on the Colorado at Lee's Ferry as a 10-year running average. And then the orange line is water use, also 10-year running average. I'll point out that water use is different than water demand. I think most people appreciate that, but when you look towards our projections, those are water demand, not anticipated water use. That's why there's a bit of a disconnect. We have a supply limited system in the Colorado, and so usually there's more demand to go around than supply in any given year. So that's why the demand is in fact higher where those 2 meet. And then we can see also that we're expecting quite a bit of uncertainty with respect to future supplies. And so really that's the crux of our study. How do we contend with and identify the challenges those imbalances will pose, and then how do we be smart about responding to them potentially? Okay, so system reliability analysis, I think this is really where it gets to some of the interesting aspects of this study. It's a bottom-up approach. So really we're focused on understanding the system and what causes it to have these adverse outcomes rather than trying to best predict the future and then see what needs to be done, right? And so we've got indicator metrics, and so a metric could be something as simple as reservoir pool elevation. And then the vulnerability threshold would be, I don't want to fall below level X. And when I do, that results in a vulnerable condition, and then we can track how often those vulnerable conditions, or excuse me, those vulnerabilities occur, and then ultimately arrive at vulnerable conditions. So what are driving those outcomes? Is it a demand-driven issue? Is it an operational thing? Is it supply? And so we can actually look at the conditions that lead to those vulnerabilities and then potentially develop signposts as precursors that would lead to action. All right, so all of this comes to what is the system doing and how might we be able to address it. And so using my example of a reservoir falling below a threshold, here we're looking at Lake Mead falling below 1,000 feet. So the metric is pool elevation, the vulnerability threshold would be 1,000 feet. And we did an analysis to look at what are the conditions that tend to lead to those Lake Mead below 1,000 events. And what I want to focus on here is the x-axis, and what we found was that the 8-year drought magnitude in the hydrology was actually very important in defining when we got Lake Mead falling below 1,000. And so all the red marks in these plots are Lake Mead falling below 1,000, and all the gray ones are Lake Mead not below 1,000. And so if we look at the baseline, which is no action, just letting the model run under current assumptions, you can see that the red marks typically stay left of a 13 million acre foot average 8-year drought. So if you have an 8-year drought that averages 13 million acre feet of average flow, most of those conditions or worse have Lake Mead falling below 1,000. And so a probabilistic approach would say if I implement portfolio A or portfolio B, how many did I reduce? Did I reduce 15 events? Did I reduce 35 events? Is it a 15% reduction? You would get that type of information. But really in this study, I think one of the really novel pieces is we moved beyond just simply how many events did we reduce from that probabilistic approach to how much vulnerability protection did we gain. And what you see here is the defining line of 13 million acre foot average 8-year drought under the portfolios now shifts. And so we've actually bought some protection. So now we can weather an 8-year drought that has an average flow of 12.6 million acre feet, and that typically is the break point between these events of Lake Mead going below 1,000 or Lake Mead not going below 1,000. And so it turns the paradigm a little bit around, and it allows you to better quantify what you're gaining by implementing options. You don't just get numbers. I reduced 15%. You actually see that the conditions that lead to this reservoir falling below this elevation have now changed by this amount. And I think that's a powerful way to look at dealing with uncertainty, because it's less about am I predicting a certain event, but rather understanding my system and how it responds. All right, so I'm just about out of time here, so I'll make a few summary remarks. I come from a modeling background, so I think models are pretty important, not necessarily climate models, but understanding your system. Being able to represent it well and understand how it's going to respond is super critical in my mind. You also have to know what your risks are and your vulnerabilities. If you don't know what you're trying to avoid, it's really hard to avoid it, right? And then in terms of the options, you need to understand their efficacy. Not all options, not all actions are going to address all vulnerabilities in the same way. You need to have that sort of crosswalk between if I'm trying to address X, I need to do Y or Z, but not W, for example. And then also system monitoring. I think many of us are always looking for more information about how our system's performing. We wish we had longer records, more data. And so if we have better monitoring, we can get that context, but we can also look for these signposts. What are the conditions that tend to lead to these undesirable outcomes, and can we do something when we start to see them rather than just waiting for the undesirable outcome to occur? And then last, we need to keep an eye on these climate predictions and projections. I am optimistic. I think they're going to continue to improve, and I think we'll be able to glean more and more information that allow us to more effectively hedge. But I think in terms of this type of uncertainty paradigm, start with what you know and what you can understand best, and then work away towards the increasing levels of uncertainty rather than starting with the most uncertain piece, our ability to project future climate conditions, and then trying to respond. So my 2 cents. Thank you very much.
Thanks, Ken. Questions for Ken? Mm-hmm. I'll bring you a mic.
Thank you. Great talk. The Bureau currently monetarily supports such community positive behavior as keeping selenium or salts out of return flows. Is there any effort to model or to implement some sort of community positive behavior, such as building soil carbon or minimizing on-farm greenhouse gas emissions?
So I think in terms of the salinity question, we do some efforts to model the impacts of different activities on salinity loading, things like that. I don't know that they've been perhaps tightly coupled with like this type of an activity where you're looking at benefits across different outcomes so comprehensively, if that makes sense. There's certainly a lot of opportunities for like synergistic investments where you can see the benefits across a variety of desired outcomes. This study was largely supply and demand kind of focused, and so I certainly would acknowledge that as a limitation. But yeah, I'm not aware of anything that's quite that comprehensive, yeah.
We have any more? All right, well, let's thank Ken again. And our final speaker before we go to the policy panel is David Groves from Rand Corporation. He's the one who brought out all the silly dice and hoops and all of that earlier. So, but hopefully you had a good experience with that, and his talk will tie that all together.
Great, thanks a lot. Hopefully this one works. Great, well, for those of you who didn't hear my introduction earlier today, I'm David Groves. I'm a policy researcher with the Rand Corporation, nonpartisan policy research organization. I've done a lot of work in Western water, worked with Ken and Lorna on the Colorado River Basin study and a little bit with Denver Water. And so what I want to do today is just wrap up or try to pull together some of the themes that came out of the game, and then also the presentations of Lorna and Taryn and Ken. So the overarching question, which I don't have to elaborate on, of course, to this audience, is how should we plan for the future when it's so uncertain? So we've got uncertain, needs and demands for water in the urban, agricultural, and natural environment. And then, of course, we've got this imposed massive change, potential change due to climate change, due to changing climate. And so the question is, how do we make decisions about this when it is so uncertain, as we've been talking about all day? And what I want to, really build on the previous talks, which were really great examples of, emerging group of methodologies that can be grouped under the, the rubric of decision-making under deep uncertainty, or DMDU. And what these kinds of methodologies are all about are, using models so that we can plan for the uncertain future by, instead of trying to predict the future, we instead ask many what-if questions. In the case of Denver Water or the Colorado Water Plan, it was, let's look at 4 or 5 different scenarios, describe those scenarios, and ask, how will our system perform under those scenarios, and what can we learn from that in terms of what decisions we might want to make today, and take that knowledge and then build that into adaptive plans. Ken talked about some applications that take that philosophy and extend it to looking at many more scenarios. And we think that all of this kind of planning under uncertainty can fall under a common framework, which we're calling here robust decision making, but really it encompasses a lot of state-of-the-art planning now for uncertainty. So key features are evaluating many futures, and then rather than trying to guess which one is going to happen or putting probabilities on it, use that instead to identify the vulnerabilities and then test different robust adaptations. And then a key piece of this is that this kind of work, and this is certainly evidenced in the Colorado River Basin study, as well as the Colorado Water Plan and Denver Water Planning, is it's a deliberative process. There's no right answer that you can, if you have the best climate science and the best model, you can just go back in a back room and come up with the best adaptation. It's really an informed deliberation, and so we want to use the best science and models to help inform that decision making. So what I'm going to do is, rather than kind of go through the theory, I'm just going to present an example, which I like to present when I'm talking about how the linkage between thinking about uncertainty and actually informing a decision for in this case, a water utility. So this is looking at a case study that was financed by the World Bank, looking at some of the water resource challenges in Lima, the capital of Peru in South America. And this, while it's a very different context in some respects, it also shares a lot of similarities to Western water issues. So a lot of water-related challenges, 10 million people, rapidly growing population, many industries. Their water supplies are, put at risk from climate change. It's a pretty arid, very arid region. I mean, 6 millimeters is actually the amount of precipitation in Lima. I know it sounds ridiculously low. It's true though. I keep looking it up every time I give this talk. And they depend on shrinking glaciers, et cetera. So there's limited water storage and drought supplies and vulnerabilities to floods, et cetera. So there's a lot of challenges, and climate and growing demand really are going to stress the system. So the World Bank commissioned an evaluation of a master plan that the region had created. So think about their $2.7 billion master plan as what they think they need to do under their prediction of the future. And we wanted to look at that more carefully. So, following sort of traditional approaches, they designed their plan by predicting or projecting historical trends forward. And what this graph is showing is demand on the horizontal axis and just changes in supply on the vertical axis. The current conditions is indicated by the red dot, and their projected future demand increasing over to the right, and no change in climate. So that was sort of their projection, and they developed billions of dollars worth of investments to account for that. And so this raises a lot of questions. That projection and growth of demand is highly uncertain. I'm just going to go over this a little bit quicker. Future climate is, of course, uncertain. And also, their ability to implement their plan is deeply uncertain. So that led this question, that we try to address is, well, how can we use methods for decision-making under deep uncertainty to help them really understand which elements of their master plan are really the foundation of a robust strategy. So I'm just going to walk through that analysis quickly as a way of illustrating these techniques, and I'm sure you're going to see themes from other talks, and hopefully they'll all kind of come together. So one of the basis of the methodology is to use models to think expansively about how the future could develop. So we're kind of building on the traditional scenario approach of 4, 5, 6 scenarios to hundreds or thousands of scenarios. So rather than just looking at one projection, we looked at a wide range of projections, loosely informed by climate science, but not particularly close. We looked at a much broader extent of demand. And the idea was, let's just see what the system can handle and what conditions would break the system and which wouldn't. So each of those dots represents a different future that we looked at. As many of you do here, we used a water planning model to help us understand how the system would perform under a particular proposed future representing the different uncertainties. So this is the brief schematic of the water system. So we ran this water model one time for each of those futures under current conditions, and then also under a bunch of different investments that were part of the master plan. From this analysis, and I'm glossing over a fair amount, but that seems appropriate for a 12-minute talk. From that analysis, we identified for each of those futures which elements of the master plan were really necessary and which elements were not necessary, and as a way of figuring out, well, how should you think about implementing the master plan. So we found out that for many futures, particularly when demand is sort of on the left-hand side of the scale there, and if conditions get a little wetter in the region, that about 6 of the 12, or I forget how many total projects, but about 6 of the projects representing about 50% of the budget would be sufficient. So there's a whole bunch in that plan that would not be needed under many, many futures. And that's really important because there's obviously resource constraints. There are another series of points in orange where an additional 4 projects would be needed to ensure reliability, and that would cost another 25% of the budget. So you're beginning to see diminishing returns. And then a bunch of futures in which no matter even if you implemented the whole master plan, you would still not achieve reliability. So those are futures in which the the $2.7 billion master plan is not sufficient, and it needs to be revisited if they're to accommodate those conditions. So from that, we haven't yet predicted the future. We're not saying which one's more likely or less likely, but we can infer a lot. We can learn a lot from it, and I think that's the key point of this methodology, is that you can often learn decision-making relevant information without having to agree on how likely different aspects of the future are. So what did we learn? We can look at a bunch of different projects that are in the master plan, are the columns in this chart, and the rows are a bunch of different conditions that are those different scenarios that those different portfolios that we identified. And what we can see here is that there are some projects that are always included, under the 50% solution or the 100% budget solution. The projects that are highlighted in green are always included. These are low regret projects. These are projects that everyone can agree, we can implement this, we should implement, even though we don't know the extent of demand growth or how climate's going to change. And so these are things that really are the foundation of a robust plan. We're also, through the analysis of this expansive looking at scenarios, we identified projects that really aren't necessary. They don't add additional value to the plan, and so you can eliminate those. And then everything else is really contingent on the kinds of conditions that we're going to face. But what we learned from this analysis is what conditions would lead to which needs and which projects should be implemented. So the last step was taking all this information and building it into an actionable, robust, adaptive plan. And so it's a little complicated here, but I'll step through this. But this is a depiction of a robust implementation plan for the utility in Lima, Peru. It starts with some near-term actions. These are those low-regret actions that we demonstrated were always useful. And then, so those are projects that they are now actively working to implement and then what the plan calls for is then evaluating the feasibility of a couple of projects that are more difficult to implement and potentially not possible. Under the cases where those projects aren't possible, different investments should be made. And so this is sort of a decision point that then leads to different midterm investments. Then the last signpost is related to climate and demand. So we've basically deferred some of the decisions deferred understanding how demand and climate's going to change about the future until we experience more of it and have better information. But then what this decision tree is showing is that at that point in the longer term, then we can look and see, well, how has demand evolved? How has climate evolved? And based on that, we have a whole set of different investments. One of the things that we learn is that there are some conditions where no additional investments are needed. We also learn that there are cases where there's additional investments beyond the master plan that are needed. And that suggests that perhaps the utility really ought to ensure that demand doesn't exceed the particular threshold, because at that point the plan cannot accommodate it. So the far right here just indicates those long-term actions. And so taken together, this is a plan that the utility can feel confident in implementing. It's going to lead them to making the right kinds of investments, and they're doing it without really having the certainty that water planners might ideally like. And I think this is really a nice example of how the method can come together, and it doesn't have to be particularly complex in the end. So a couple key takeaways. Climate change and other uncertainties clearly complicate planning, and these new decision-making under deep uncertainty methods, like the scenario planning and robust decision-making versions, can really help explore what could happen and then identify, how we should adapt. A take-home is really, emphasizing that we're trying to identify solutions that are robust, that will perform well regardless of the future. That was a theme in the game. That was a theme in Ken's presentations and the others. And then lastly, and we didn't talk about this too much, but again, these types of analyses, you should think of it as planners. These are decision aids. These are not trying to designed to tell you what you should do, but rather inform your decision making. So with that, I will take questions. Thank you so much.
Thanks, David. Questions? I'll ask one to start. I mean, this sort of framework, and you've got these check boxes. It all makes a whole lot of sense when you look at it. But I would say, you know, maybe to put it diplomatically, when it comes into the political realm, sort of thoughtful deliberations and things like that are not always the way that things go about. I guess, what was your experience with that in Peru, and is that different politically than in the U.S.?
Yeah, I mean, I think that, you know, these kinds of analyses always point out trade-offs that are, you know, one always needs to balance how much, you know, robustness do you want to invest in versus how much, you know, investment are you willing to make. There's also, you know, this was a very, you know, pretty one-dimensional problem focused on water supply, but, you know, obviously in the Western water context, there's lots of different objectives. You know, the basin study looked at a whole slew of them, for instance, in the Colorado Water Plan as well. And oftentimes there are trade-offs. So the analysis is not trying to tell you how to balance between different needs and objectives, but rather just present the information. Say, well, if you value, you know, this particular, you know, supply or this particular environmental attribute more than something else, here are the kinds of decisions that make the most sense. And then by understanding that, then you can look for common ground. And that's really the basis for consensus and cooperation. And we find that this kind of methodology, despite its being pretty analytical and complex, it actually helps support those discussions.
You just want to? Yeah. Oh, I'll run back there.
Thank you. I enjoyed your game today. That was on the decision-making flow chart for Peru that you showed. I was having trouble reading it, but it seemed like every step of the way was one of the answers reservoirs, additional reservoirs. Is that what I was reading there? Or what was
in the decision tree?
Yeah.
Yeah, in the Lima context, additional surface supplies was one of the, you know, more expensive and potentially contentious options. And so what we were trying to do is determine, is that a decision that needed to be made today, or is that something that could be deferred until later? And we found out that yes, it could be deferred until later, but these were the conditions in which it would actually be a required investment.
Thank you.
Mm-hmm.
Any last ones? All right. Well,
Great. Thanks very much.
Thanks, David. And let's give a round of applause to all of our speakers from this part of the session.